Okay, welcome back guys. Today we're going to be talking about potential difference, the conversion from electron volts to joules, they're both energies, the uniform acceleration inside an electric field like the one we've got set up here, and the application for this section, which is the cyclotron. So to start with, delta V, or potential difference change in voltage, is defined as the work done per unit charge on a small positive test charge. The same small positive test charge that we're dealing with when we're talking about the direction of the electric field and those sorts of things. Okay, so the change voltage is defined as the work done per unit test charge. Alright, and what you will most likely see it as is this formula. Work is Q delta V. W equals Q delta V. The work done by moving a charge through a voltage. So this voltage here is set up between plates. That sets up an electric field. This voltage here is similar to the distance that you would move an object, lifting up a brick, for instance. So lifting up something through a voltage, through a distance, is the same as charge through a voltage, and it takes energy to actually do that. So what you've probably seen before is energy, potential energy, is mgh. This M is related to, is the physical property, that's the charge. The GH is how far and against what sort of field is the voltage here. So what you've got is the work done to move, an electron through a volt is equal to an electron volt, this guy here. Alright, so generally you would talk about the charge of an electron, you would talk about a certain number of volts, and you would end up, say, moving an electron through, let's go 10 volts, and what you would do is say, alright, well, W equals Q delta V, W equals Q delta V, and in this case here, Q of an electron, the voltage, and what you'll get is some nonsensical answer like 1.6 by 10 to the minus 19 minus 18 joules, and you're probably going, oh my crap, what the hell is that? It's a kind of, not a nonsensical answer, but the same way we change kilometres an hour to metres per second, or metres per second to kilometres an hour, so it makes sense. 27.8 metres per second is about 100 k's an hour, but no one says you drive down the road at 27.8 metres per second because it sounds like a twit. Neither do we say it takes 1.6 by 10 to the minus 18 joules to move an electron through 10 volts because it sounds like a twit. What we do is we convert. So 1 electron through 10 volts is 10 electron volts. If I had 2 electrons, 2 through 10 volts, that would be 2 times 10, 20 electron volts. That would be similar to moving something, lifting something up 10 meters. Instead of lifting up one thing, you're now lifting up 2 things, so it takes twice as much as it did before. Same sort of idea. So it's all just energy. Work done is energy moving something from one place to another, and in this case the electric field, or the potential difference, will actually do that. Inside this field, so inside here, we have an electric field set up because of this change in voltage, and what we can say is Newton's, let's go to this colour, Newton's second law, F equals ma. F is always ma. Looking for any other. No, we're good. Oh, hang on. And technically, there we go. Now we're good. F equals ma. It is also equal to EQ. So the electric field strength times by the charge requires a force. So this is the same as, so F equals ma, the property of the field, acceleration due to gravity, electric field strength, so field, and then physical property mass, physical property charge. So now we've got these two ideas related to each other. Ma equals EQ. Remember, it is a physical thing. It's a proton, it's an electron, it's a hydrogen, no, I won't say hydrogen atom, ion, because that's just a proton, helium nucleus, something like that. So we've got a charged particle, we know the size of the charge, we know its mass, it is a physical object, we can calculate its acceleration. So what I'm going to do is rearrange, and I'm going to get the acceleration, the acceleration of that particle, EQ on M. This number here will be massive, simply because, so charge is 1.6 by 10 to the minus 19 for electrons and protons, but the mass is minus 27 for a proton, minus 31 for an electron. All right, electric field strength probably a few thousand, but this charge to mass ratio incredibly tiny. That's why this thing is way more powerful, I guess, than gravity, which is why we don't worry about where gravity is and what gravity's doing. So what we can do is move this charge through here. So if I have a positive charge, we're going to call it a proton, as it approaches this field, it's going to experience an acceleration because it's going to experience a field which creates a force. So it'll experience an acceleration because there's a field which applies a force. And the force in this case is going to be uniform, and it's going to be directed straight down from the positive plate to the negative plate. So the path of my projectile, hopefully I don't mess this up too much, path of my projectile, if it comes in at perfectly horizontal, it will go this way. Except here, remember, dead straight because it's outside the field. So that's going to be the path of my projectile. My proton. It is a projectile. Remember, the acceleration is only in one direction, just like gravity. There's no horizontal component to it, so it doesn't slow it down or speed it up horizontally. There's also no wind drag. So it's perfectly projectile motion, which means that we can use the same projectile equations. And in this section of the course, one of the key questions, or one of the major questions you'll be asked, is what's the deflection of that particle? Okay, so the deflection of that particle is related to the size of the acceleration and how long it's inside the field. And the process that you'll have to go through is this. The electric field strength, you will be either given it, you'll be able to find it, change in voltage over the distance. You will be able to find out the force, which is EQ. This here is F over M, so F equals MA, I've just rearranged it. The time is going to be related to V is S over T, so we know how fast it's going, so we'll be given the speed, you know how far it's got to go, so you're going to be able to work out how long it's going to take, and therefore T is S over V, something like that. And the deflection here, so this distance is the horizontal one, this is the horizontal speed, this is the horizontal but also the vertical time, V I T plus half a T squared. That will disappear because I'm not mean, and that is the thing that you'll have to plug in from here. You'll be able to work out whether the particle actually deflects far enough to hit the bottom plate or whether it makes it through. Now the application for this course is this thing over here, the cyclotron. Alright, kind of looks like a hamburger. We call these two things the D's because there's two of them, and they're kind of D-shaped. If you tilt your head left and right, you'll be able to pick that up. And what we have is a alternating pair of plates, just like up here. Outside the plates, remember, down this way and up here, we don't have any field, so nothing's happening up there, it's only between the plates. So if we started off with a positive charge here, it would be accelerated away from the positive one towards the negative one. In here it will do a circle because there's a magnetic field, we'll get to that later, and then the polarity of these things change and it accelerates again and again and again, and so on and so on and so on, until, perfect circles by the way, not like I'm drawing here because I'm in a hurry, until it's going fast enough that it will exit that thing. We use these things for, I don't know, creating radio isotopes. Oops. So radioactive isotopes of elements, so we can use them for medical diagnostics. Alright, so every time there's charge goes through the gap, work is done on it. If work's done on it, that's energy. That's related to speed because KE is half mv squared. That's terrible. Alright, so application, some general types of equations that you'll see, and this question here will probably come back a few times. Alright, any questions, come see me.